ABC Listen. Podcasts, radio, news, music, and more.
At the centre of our Milky Way lies a supermassive black hole. This black hole lives in a part of the sky that Dr. Laura Driessen looked at as an undergraduate science student, poring over data from a giant radio telescope to create images of what that black hole and the centre of our galaxy might look like to the human eye. And it's quite beautiful. Around the blackness there is stardust, flares and bubbles, and twinkling streams of light. If you left this supermassive black hole and travelled past the constellations of Sagittarius and Scorpius, where the Milky Way appears the brightest, and kept going south to the Pipe Nebula, and on and on and on about 26,000 light years, you would finally get to us here on Earth. The scale of the universe and the wealth of information it holds fascinates Laura, who is now a radio astronomer unlocking the secrets of the stars at the Sydney University's Institute of Astronomy. Hello, Laura.
Hi, so happy to be here.
So, at the center of our galaxy is this giant black hole, as I said. My understanding of black holes comes mostly from pop culture, which means I imagine they suck everything into them and whatever goes in never comes out again. Is that correct? And if so, are we being sucked into the center of our galaxy?
Well, it is true that once you're in, that's kind of it.
Okay.
So I don't recommend it as a general rule. But no, actually, we're not being sucked in at all. So black holes are really heaps and heaps of gravity and mass kind of squished down into basically nothing. But if we imagine that the sun turned into a black hole, it won't ever turn into a black hole. But let's imagine for a second that it does. All the planets would stay in their same orbit because the gravity of the sun hasn't changed. So just like we're not being sucked into the sun, we're staying in a nice orbit around it.
Okay.
We're not being sucked into the centre of the supermassive black hole, only if you accidentally get too close.
Okay, right. And so a black hole is created when a star dies, right?
Yes, when a really massive star dies. So stars at least 10 times the mass of the sun. They have very short, in astronomy terms, so still many hundreds of thousands of years, they have very short lives. And eventually the light pushing out, the energy pushing out, can't keep up all the matter on the outside. And then it all just falls in and goes boom.
And so if black holes aren't sucking everything into them, why is there such a warped understanding of black holes in pop culture then? Where does that idea come from?
Well, we should start with the name because they're not holes. I think that's probably one of the most difficult things to explain because it's when people say what's on the other side of a black hole, I'm sort of like, well, you just walk around it and there's more space. Because it's not a hole. It's more like saying what happens if you go through a bowling ball. You shouldn't do that. And also it would be really hard. So they're not actually a hole in any sense of the word. We call them a black hole because in space they do look like blackness, like nothingness.
Okay.
So that's probably where the problem starts.
All right, so what do they look like then? Tell me more about that. Are they circular? Is that where we're getting the hole from?
Well, yeah, they're roughly circular. If they're spinning, things can look a bit different. But when we see a black hole, we're not actually seeing the black hole itself. We're sort of seeing what is the edge of its influence. That edge is the point where gravity gets so strong that not even light can escape anymore. So it's not the surface like we think of a surface, like the surface of the Earth. It's the edge where you can't escape anymore.
So the edge of the blackness.
Yes,
of the
edge
hole,
of the
not hole.
Yes, the not a hole, but is black. Yes.
We'll stick with black hole for now.
Yeah, exactly.
And so you created an image of this black hole at the center of our galaxy. How did you get to see this in this part of space?
Well, so I actually created an image that's not the black hole itself, though astronomers have done that since. It's the area around the black hole. So this area is just a really crazy area. And the reason that we can't see the black hole itself is it's actually really small and very far away. So as you said, it's about 26,000 light years away. That's a pretty great distance, and there's a lot of stuff going on around it. So we need a really big telescope to see the actual black hole. But the area around it has a whole lot of stuff going on.
Like what?
So a lot of exploded stars. So this area is really energetic. There's just a lot of things going on, probably because of the influence of that supermassive black hole. So stars live and die, and we don't get to see them actually live and die. Our lives are way too short to see that. But we know this is happening because we see stars at sort of all stages of life, from young stars to very much dead stars, which look like these big bubbles of light in space. They're called supernova remnants. And we have these big streamers that we call filaments, and we don't know how they're made or what's going on with those, but they look like these big sort of strings of light across this area. So there's a lot going on and there's a lot that we still don't know.
Can you just explain for me again so I understand it? Why is this such an active area around the black hole? What is it about the black hole that's making all this birth and death happen?
This is a really good question. I actually don't know the exact answer, but we see using these big telescopes like the Very Large Array, Meerkat, the telescope I used was the MWA, that we just see all of this stuff happening. There's probably another astronomer out there who could answer that question in more detail with modelling and all that sort of stuff, but all I know is it's very exciting to look at.
And so you created an image of all this stuff happening around the black hole as an undergraduate, which is pretty incredible. How accurate were those images?
So the actual structure, so the shapes and things that we could see in there were pretty good, but the brightnesses were probably a little bit off. So I wouldn't have used those images for specific science, and they were remade as part of a big survey. But as a student, still an undergrad, it was so amazing to see that the data that I used turned into these amazing images that would later be maybe improved a little bit and then used for some science.
So you mentioned you use a radio telescope to create those images, the data captured by that. What is a radio telescope?
So a radio telescope is a telescope that captures radio light. So when we think of telescopes, we kind of think of the ones that maybe we put our eyes up to. So that's the kind of light that we see with our eyes, which is called optical or visible light. But there's a whole bunch of other kinds of light, right? We have X-rays, which probably some of you have had an X-ray before. That's a kind of light.
I don't think I knew that it was a kind of light, but okay.
It is. It's a kind of light. X-rays are a kind of light. UV, that burns us a lot from the sun. That's a kind of light. Gamma rays, they're a kind of light. But down the other end of the spectrum, so that's all down the blue end, the kind of high energy end. Down the other end, we've got red, and then you have infrared, night vision goggles.
Yep.
Microwaves, literally the kind of light that heats your food up in a microwave
Light heats
oven.
your food?
It does.
Okay.
Yes, and this is an important part of the story later as well, because it
Okay.
caused a few problems for our radio telescopes, the good old microwave oven. And then we keep going down and we end up at radio. So it really is kind of, the way that I think about it is that it's the base of light. So if you think when your neighbor is playing music really, really loud, you can always hear kind of the subwoofer.
Oh, yeah.
But you can't necessarily hear the high-pitched sounds.
Right.
And that's why radio is so good. It goes around and through things just like the bass. So it's a kind of special low-frequency type of light.
So it's the light you can pick up when other types of light won't make it, or?
Yeah, that's right. So in particular, the dust and gas that we have all through our Milky Way. So if you're lucky enough to be in the southern hemisphere and you look up at the Milky Way, you'll notice dark patches, and one of those is famously called the dark emu. And those dark patches are actually dust and gas in our Milky Way blocking the light of stars behind. So with an optical telescope, with the light that we can see with our eyes, we can't actually see the center of our galaxy at all because it's just blocked, it's obscured. But radio light doesn't really care about dust. It just goes straight through. So that's why we can see the center of the Milky Way, and also we can see very, very far distances with the radio.
So this image I'm getting in my head, or the analogy, is like it's like a heat sensor. It can see stuff that you would otherwise wouldn't. Is that kind of correct?
Yes, that's it. And that's why we use all these different kinds of light. In astronomy, we don't just go for one type of light because you would be missing so much information. And every kind of light is actually made through a different kind of physics. So we think of light, maybe heat is one way that we think of light being made, like the sun or a candle. But there's actually lots of other ways that you can make light, and we see those at all the different frequencies.
The other question I have about radio light is the radio you're talking about not the same as the radio, we're broadcasting on, unless you're listening on podcast. But yeah, are these two different types of radio we're talking about?
Sort of. This is the problem with historical naming of things. So radio light is the light that is used for Wi-Fi, Bluetooth, the way that radio waves, so the way that someone at home turned on their actual radio, it was receiving signal as light. And then the actual mechanics would turn that into sound. So radio is all connected through radio waves of light.
So when did we find out that radio waves actually come from space?
Humans have been looking at space forever, right? So it kind of feels like we've known that there's light from space forever, as long as we've had eyes, really. But we've only known that radio waves come from space since the 1930s. I think it's about 1937. And that was through telecommunications. So Carl G. Jansky was a telecommunications engineer, and he noticed that all these radio operators, there was always this constant kind of fuzz in the background of the radio when they were trying to communicate with each other, and he was trying to fix it. So he was trying to just work out what was going wrong so he could make everything beautiful and smooth. But he noticed that this fuzz would get louder over the day and eventually worked out that it's actually the Milky Way as it goes across the sky. So we were hearing, because of the way that, just as we were talking about radio being radio waves translated into sound, we first heard the Milky Way when that light was translated into sound.
So is that what I'm hearing when I'm tuning the radio and I hear fuzz now?
Yeah, well, it's a bit of everything. So we've got a lot of things around us that create radio waves. So we talked about phones, GPS satellites, that's all radio waves, how we communicate to satellites in space. So there's a lot around us. But yeah, some of the fuzz when you're tuning an old school radio, that is from space.
Take me back to little Laura now. Where did your interest in the sky begin and where did you grow up?
So this is all according to my mum because I was 4 years old, so I don't remember it, of course. But I went to my local library, or my mum took me to our local library, which is the Croydon Library in Victoria. And they had a school holidays program with an inflatable planetarium. And apparently as a 4-year-old, I went in, crawled into this little inflatable planetarium and came out, and that was kind of it for me forever. It was always going to be space from that moment on.
Oh.
And I think we think about astronomers maybe as people who love looking at space with their eyes and working out exactly where every constellation is. And that's an amazing thing to do. Amateur astronomers are very helpful to astronomers and it's great fun. But that's never really been my thing. I've always appreciated how beautiful space is, but I've never wanted to know exactly which star was which.
Okay.
I wanted to know how it all worked. So I was more interested in kind of the details and the study of these things.
And what did the starscape look like where you lived and where you grew up?
It was really beautiful. So I'm from about 45 minutes drive out of Melbourne in a place called Wonga Park, which is the outer eastern suburbs. Even people from Victoria haven't heard of it. So it's a little bit out of the city, enough out of the city that you definitely get a beautiful view of the night sky. And we used to go on holidays to rural Victoria as well a lot. So I got a lot of really good views of the night sky.
And so did your parents give you like a telescope to encourage this, fascination?
They did. I got a telescope. I couldn't tell you what age I was. I think still primary school. And I remember that we set it up. I think we were in Malakuta. And the first thing my dad pointed it at, because he knows all of these things, was Saturn. And to be able to see Saturn's rings with your eyes, that was just mind-blowing. So as a little kid, and I think, just pointing at everything. But Saturn really, most things in space are dots. But Saturn has these beautiful rings. So that really captured my imagination as a kid.
So you said you weren't the kind of kid who wanted to name every constellation. That wasn't your particular obsession. You just wanted to look and understand.
Yeah.
So, how did that sense of wonder and interest manifest? Was it just, through staring through your telescope all day long or all night long?
No, so it was probably more doing school projects. So
Okay.
anytime there was a science project, if I had a choice, I would choose something in space to investigate. I remember one of the earliest things that as a kid you'd call a big project, so still pretty small and adorable. I did on Pluto, and that was before it was downgraded.
Oh, right. Okay.
It's still my favorite space object.
Why?
I think as a little kid, I just thought it's so far away, and that's just amazing. And of course, now I know it's not actually
Now
that
you're looking
far
at a
away.
black hole 26,000 light years away.
Yes. And my favorite planet is Jupiter, so that has switched a little bit.
Okay.
But I did do these sort of detailed investigations. So I really wanted to know how everything sort of worked. I think I didn't really even understand what that question meant then, right? But I really wanted to know the details.
What did your parents do for work? Did you come from a line of scientists?
No. So my dad is science adjacent. He's an engineer. He's a manufacturing engineer. And my mum is actually a sales rep. And I'm the first PhD in my family. My twin sister beat me at being a doctor because she's a medical doctor. So she got there a few years ahead of me. But we don't have scientists in my family, a lot of amazing people, but no, I'm not scientists. But having an engineer as a dad does kind of give you that, how does the world work? And I remember making things like little circuits to make a little alarm as a kid, welding soldering little things together, or making a birdhouse and really thinking about how things come together and how things work. So that was definitely part of it. And I think my communication comes from my mum. She's really good at connecting to people.
And so with your twin, who's a doctor, how similar were you guys growing up? And was there a bit of competitiveness between the two of you because you had similar interests?
I wouldn't say competitiveness. I actually think because we also played a lot of tennis when I was a kid, and I think it was more stressful when we had to compete because it's hard when you both want to be successful, but you both want the other person to be successful as well. So I think that's been really helpful in my science journey as well, to realize that in a lot of cases, you're not actually competing directly with someone. You're actually both working towards a goal. And when one of you succeeds, kind of everyone succeeds as well, especially as a woman in STEM. I really feel that collective lifting up. So I have to say we weren't competitive, because really if I get 10 out of 10 on a exam, she can too. So it's not really like, and we all three of us got very good grades. So I think there wasn't really that competition. We don't feel that. But my parents were great. They put us in separate classes. So we did kind of develop our own identities. You see a lot of twins that are kind of
that's interesting. They put you separate.
Yes, it was very deliberate. And we were never really dressed the same or anything like that. I think Mum realised early that we would always be best friends because we spend a lot of time together. So we do say the same things, which is more annoying now because we live separate. So when we come back together, we're not as practiced at saying different things.
Are you identical?
We are identical, yeah. So it really helped both of us to be separate during the day, make our own friends. But of course, our friend groups ended up merging in the end. We are very similar people.
And so, okay, you were this young child with this interest in the sky and space. At what point did it occur to you that you could actually grow up to become a scientist?
Not until I was nearly grown up.
Right.
So I think it's one of those cases where you sort of know that astronomers exist, but it takes an extra moment to realize that you could actually be the astronomer. So the idea that if you can see it, you can be it kind of feels a little bit, deep and meaningful. But it really is true, and I've experienced it. So I was at the Professor Harry Messel International Science School at the University of Sydney. I did my high school in Melbourne. So I was 17, year 11, and went up for 2 weeks. And I don't think I've told him this, but Professor Geraint Lewis, who is still a professor at the University of Sydney, gave a talk on cosmology, and he showed these big dark matter simulations. And it was him, but I think it could have been any astronomer. It was that real light bulb moment that I went, wait, he does this every day. Maybe I could do this every day. So it wasn't until I was 17 and already sort of on that path that I realized. And I was told that as a woman who likes science, I should be a doctor, which obviously is great. My twin sister is one. But
who told you that?
Well, the career advisors at school, I think being a scientist is not necessarily something they jump at.
Okay. So if you wanted to be a scientist, it meant you had to be a doctor to them.
Yes, a medical doctor.
Okay.
And I think at that point, though, I sort of hadn't really realized I wanted to be a scientist either. But yeah, definitely didn't hear you should be a scientist when I was a teenager interested in science.
And so Professor Grant Lewis changed your ideas about that.
Yes, exactly. And I still remember those dark matter simulations. I think they've improved now.
You said he's a cosmologist. What is cosmology?
So there's different kinds of astronomy. It all comes under this big umbrella of astrophysicist. An astronomer is the observational kind, so we actually look at space. Then there's theoretical and also cosmology. So cosmology answers sort of the big questions. How fast is the universe expanding? How did it start? What's the structure of the universe? Rather than our Milky Way itself, how do all the galaxies kind of connect to each other? So it's those really big, deep questions that are a bit scary to think about.
Is it a lot of physics and maths rather than looking through telescopes kind of thing?
Yes, it is. It's a lot of simulations and modelling. So they'll often use a big computer to do a big simulation, and then they'll ask us observational astronomers, like, can you see that so we can prove that what we thought about was true?
So did you initially then want to be a cosmologist as opposed to an astronomist?
Yes, I did. So I sort of initially thought, because I love maths, and I actually didn't do very much physics. So if there's anyone out there who wants to do astronomy but doesn't maybe love hard physics, it's still possible. I did in undergrad, and already earlier I knew that I loved maths. And so cosmology is a lot of maths. It's really a lot of maths to kind of understand the universe. So I really thought that that was what I wanted to do until, as an undergrad, I did this summer research project and really got my hands on actual observations of space.
Yeah, tell me, what drew you away from cosmology to not astrology, to astronomy?
It was really this having data in front of me and turning it from numbers into these beautiful images that will help us understand the universe. And interestingly, I think if I hadn't done radio astronomy as a summer student when I didn't know anything about astronomy, really, I probably wouldn't be one, because radio astronomy is considered one of the hardest and kind of scariest kinds of astronomy because it's a bit different to all the other types. We're not dealing with photons and what's effectively a camera. We're dealing kind of with electricity instead. That's what our telescopes really detect in the end. So things are a bit different in radio astronomy. If you take a picture of the sky, it actually just comes out as numbers and then takes hours to turn into an image of the sky. So, but really looking at those images and using telescopes from all over the world that I wasn't right next to changed my thinking of maybe I actually want to look at space rather than just thinking about space. Now I do a bit of both.
You ended up getting your PhD in radio astronomy, searching for things called radio transients. What is a radio transient?
Well, we do this in astronomy a lot. We use words that mean something else and we're like, we're going to use it. We're just going to change the meaning completely though. So a transient is something that appears and disappears. So when we look up in the night sky, we think of things that like kind of stay the same. Like every night, everything pretty much looks the same. But actually things change. And a lot of things change on really long time scales. But what I'm looking for is things that we can actually see as humans. So things that change from as short as milliseconds to maybe a few years.
And why is that interesting, those changes, those transients?
So usually it means that something kind of energetic or bright has happened because these things in space tend to change on slow time scales. Everything is kind of slow. When we see something that goes boom, it usually means something exciting and interesting and explosive has happened.
So what kind of things have you seen then?
So I did my master's in Amsterdam and I actually worked on supernova remnants. So that's the leftovers from exploded stars. So even though I wasn't looking at the explosions themselves, I was looking at what was left over. And now I work on stars, but I also look at fast radio bursts. There's really a whole range. My main topic is stars now, flares in particular. When you work on transients, you never really know what you're going to get because you see a flash and then you look at it and you have to work out what it is. So I'm an expert more on stars, but often I'll see a flash and then find out that I'm looking at a black hole binary or something, and now I have to be an expert on something completely different because we've seen a flash.
So when you look through a telescope or look at the data a telescope collects, you're never looking at things that are happening at the moment. Like how far in the past are the things that you're looking at?
It's a bit of a range. So some of the stars that I see that flare, actually the closest star other than our sun, Proxima Centauri, which is about, I think it's 4.2 light years away, that one flashes. So the closest star to us actually flares because it's very magnetic. But we see things all the way out to distant galaxies. So we see something called a tidal disruption event. And that's actually, as we were talking about earlier, when a star gets a bit too close and gets ripped apart by a black hole. So we can see things from very, very close to really, really distant.
I guess the thing I'm wondering is, when you look in a telescope, as we said, the things you're looking at happened a long time ago because it takes a long time for those bits of light or whatever else to travel to us here on Earth. So when you look through a telescope, are you kind of time traveling?
Yes, we are time traveling. And with radio telescopes, we can time travel basically further than any other type of astronomy, especially with these energetic things, because there are a lot of things in space that we can't see because on a normal day for that thing, it's too faint for us to see. But then it has this big explosion or a flare and suddenly we can see it. So it's usually more distant than kind of the normal things we see just bubbling away.
And so what was the radio transient that you worked on during your PhD using a South African telescope?
So this is a bit of a fun story because when I first started my PhD, my supervisor said, "Hey, Laura, you should probably do a bit of background research on stars." And I hadn't worked on stars before. And I said, "Oh, but stars are boring."
What?
Because, I know. Okay. Because in radio astronomy, it's not really until recently sort of considered an exciting field. It's sort of like stars. Surely we know everything about those. They're close. Whereas in radio, we're often looking at black holes in the centers of distant galaxies. So a star kind of does seem a little bit blasé compared to that. But then he signed me up in a collaboration, an international collaboration using the Meerkat telescope in South Africa to be kind of their star person.
And so what did you see?
Well, they discovered a transient when they were just testing the data and it turned out to be a star. So they just said, "Oh, okay, Laura, we'll look at that." And it turned out to be the first transient discovered with this new telescope, Meerkat, at the time. So it was a flare from what we call an RS Canum venaticorum.
What? Please explain.
Astronomers in Latin, just best friends. So we call them an RSCVN because it's a bit less of a mouthful. And it's a binary. So it's two stars with a giant star, so more massive and bigger than our sun, with a companion that we actually couldn't see, so it was too faint. And they're orbiting around each other, and because they're orbiting, that big star is rotating. And that creates, we're getting into the technical details, that creates a big magnetic field. So this star is like a giant magnet in space. And when we have big magnetic fields, there's a lot of activity, like solar flares that create aurora. And then we see these big bursts of radio light. And it was the first time this telescope had picked up something that had changed in the sky. It was brand new at the time, only been observing for less than a year. At the time in 2018 that we first saw this transient. So we were the first ones to see something flash.
Podcast. Broadcast. This is Conversations with Sana Kadar.
So Laura, that flash you saw during your PhD research, that transient, was this binary star system where the two stars were revolving around each other and the bigger one flashed.
Yes.
Okay.
And this is very much on human time scales because they're going around each other every 21 days, which is actually very, very fast because stars are big, right? So that sort of speed when you're absolutely huge, it's pretty intense.
And so what is a binary star system? Is that a common thing?
It's really common. So a lot of stars are binaries. So a lot of stars form in pairs. Stars are formed when a big cloud of cold dust and gas kind of starts collapsing under its own gravity. And then as it's collapsing, that heats up and turns into a star. And they tend to form in pairs. So there are actually a lot of binaries.
Twins like you and your sister.
Exactly. And when one, they even though they were born at the same time, they're often slightly different masses, and that determines how long they live for. So they're often not exactly the same over time.
So if stars die and become black holes, does that mean you have binary star systems? Can you also have binary black holes?
You can. So you can have all the combos, really. So you can have a star with a black hole, and those are called X-ray binaries because the
one star and one black hole revolving around each other.
Yes.
Okay.
So they're going around each other, and we see it as an X-ray binary if the black hole is kind of pulling slowly over time material off its friend, so it's kind of slowly destroying its partner.
So it is sucking
It
stuff
is because
in
those
from its
ones
friend?
are close.
Okay.
So they're close to each other. So they're when you get a bit too close, that's
Then
when
you get
things
sucked in.
Yeah, that's when things get dangerous. But it's not like one big moment. It's over thousands and thousands of years. It's just pulling material off. You can have a black hole binary, and that's what we detect as gravitational waves. So they eventually get closer and closer to each other, and I say they go bloop and kind of turn into one. It's called a chirp, but I feel like bloop feels a little bit.
That's quite cute.
It is, isn't it? And you can also have like a black hole and a white, well, can you have a black hole and a white dwarf? I suppose, why not? But you can have a black hole and a neutron star, which is another way that a star can die as a neutron star. So you can have black holes kind of paired up. They can also be on their own, but they can be paired up with almost anything. And these aren't supermassive. That's important.
I need to ask, I mean, this might take us in a long tangent, but what is a neutron star and what is a white dwarf?
Oh, even better. So a neutron star, when a massive star explodes, it can either turn into a black hole or a neutron star. A neutron star is really dense, so it's only about the size of Melbourne or Sydney. So really small, but heavier than the sun.
Oh, wow. Okay.
So really, really dense. And we don't really know what's going on inside them because that's kind of crazy. That much stuff in that much
But they're
space,
not black holes.
They're not black holes. And we see them because some of them have like a beam of light coming out of them and they spin. So it looks like a lighthouse. We see a sort of a blip of light go past us as these spin.
So stars emit light, but this neutron star also emits light in a different kind of way?
In a different way. So
Okay.
it doesn't have fusion. So what makes a star burn is nuclear fusion at its core, and neutron stars aren't doing that.
Okay.
So I think of them as sort of zombie stars because the star had to die for that to be formed. A white dwarf, on the other hand, is a really hot, small star, but still a star in the normal way of thinking about them.
So coming back to the binary star system that you observed as part of your PhD, could you find a reason for why it was flaring?
So we think it's because of these magnetic fields. And these are now I've done a bit more work, they're relatively common. So this one was a bit interesting because we couldn't tell what the other star was. So we knew that there was another star there because of the Doppler effect. So we could see red and blue light. So we could see that there was something there. It was going around something, but we couldn't actually see what that something was. So there's still a little bit of mystery about that one. And we think it could be interesting, but I think we're going to need a really big telescope to work that one out. I'm not sure if it exists. So there's still a lot of interesting questions about that particular system. And now I guess I'm more interested in how it fits in with the bigger picture of radio stars in general.
Well, the question I'm wondering is, does any of that have any impact on us here down on Earth? Or is it just an interesting observation learning about, how space works?
So right now, that kind of star, thankfully, doesn't have an impact on us. It helps us think about a whole lot of different physics questions, because how they create this radio light and even those magnetic fields that we talked about, how those are made and what kind of star makes those. If I look at a star and you give me all the other information, how hot it is, what kind of star it is, if it's in a binary or not, we still don't have enough information to kind of say, do we see those magnetic fields or not? So there's a lot of questions about the real detailed physics of how those magnetic fields are created for all the different kinds of stars.
Tell me about the work you're doing now, the Sydney Radio Stars Catalogue. What are you looking for?
So at the moment, I'm looking for more of these radio stars.
Okay.
So a radio star is a star that emits radio light. And we talked already about how we think about light as created by heat. But the radio light that we see from these stars is created by these magnetic fields. So it's actually electrons moving around in magnetic fields that create radio light. So if the sun we see in the radio, but only because it's right next door. If we moved it to any big distance, we wouldn't see it in the radio
So
anymore.
hang on, our sun is a radio star.
It is, yes. It's just a very faint radio star. So the aurora that we've been seeing a lot, which is nice, really nice, beautiful, is actually because the sun is magnetic. So it has these magnetic fields that create these big flares of light and plasma. And then when they hit our magnetic field around the Earth, that's what gives us the aurora.
And so, okay, if the sun is a radio star and we don't normally see radio stars with the human eye, we see the sun because it's so close to us?
Well, we
why do we
can't
see
see
it?
the radio light from the sun. So with our eyes, we can't see it.
Oh,
we
okay.
can't see it.
Okay, the
But our
radio light it
telescopes
emits is,
our telescopes can see it, but our telescopes can only see it because it's close. It's actually a very weak radio star, which is good for us. We would be dead if it was a strong radio star. A happy note.
And so why are radio stars important? Like, obviously the sun's important, but what do they tell us about the universe?
So for astronomers, it's a lot about that physics. And we also want to kind of understand the population of these things. Which ones? Where are they? All those sort of big questions are really of interest to astronomers. But there's another part, which I think is probably even more fun. There are a lot of astronomers who are looking for what we call habitable planets. They're not radio astronomers, different kind of astronomy, but they're looking for planets that are like Earth, really, because that's all we know as far as habitable. So they're looking for planets that are orbiting stars where the planet is close enough that it's not too hot, not too cold, and water is wet. So that's sort of the very basics of what we call the habitable zone. But planets orbit stars. So we have to think about the star itself as well. And I just said that if our sun was a radio star, we would all be dead. So if we're looking for these habitable planets, we really don't want to be looking at the stars that I find. But we don't have
eliminate your stars.
Exactly. So it's sort of a process of elimination. Which ones do you want to live next door to? Which ones are probably not so good? But because we don't have a good understanding of which stars are radio stars, how many, and if you sort of pointed to a patch of sky and said how many radio stars are in there, we don't know that. So we don't have that information yet to tell these planet hunters, maybe you shouldn't look at that one. That's probably not the place for habitability. So I'm trying to build up this picture of radio stars in general so that we can then kind of share that with all the other astronomers, because it has impacts on the work that's being done.
Remind me, why don't we want to be near a radio star? Why are they bad for habitability?
A few reasons. So like our sun as a radio star shoots out chunks of plasma that for us just create pretty lights.
Right.
If it was one of these strong radio stars that we can see at big distances, those chunks of plasma would be huge and very powerful, and it would be hitting our planet, and our magnetic field probably wouldn't be able to take it. Plasma is not good for us. But radio stars also tend to be what we call X-ray stars. So when the sun does a flare, it also flares in X-ray. And I don't know if you know this, but X-rays are not good for humans.
I did know that.
Yeah.
Right.
So that's why you wear leather for X-rays. And it's the same reason, one of the same reasons we wouldn't want to live next to one of these stars. And the extra part on top of that is these stars, because they're active with this plasma and things going on, they're probably stripping the atmosphere off planets. So we need an atmosphere to live. Breathing is nice. But if this planet is being bombarded constantly, then it's kind of pulling that atmosphere away, just blowing it away as the star is active.
So if you're an astronomer looking for other possible habitable planets, what kind of star do you want to be looking for then?
There's a little bit of mixed wisdom on this. So one of the main stars we look at is M dwarfs or red dwarfs. So these are cool stars and they're really small. So the habitable zone where water is wet and all that is actually inside the orbit of Mercury. So they're really close to that star. We also look at these because they're the most common type of star in the whole universe. And they tend to have a couple of planets. So it seems like win-win-win, right? They're common, they all have planets, and you can the planet's really nice and close in. But M dwarfs also tend to be radio stars. We see them a lot as flaring radio stars. So they tick all the boxes in one way, but maybe not in other ways. And because the planet is so close to the star, it would actually be inside the star's magnetic fields. So that probably isn't a good time either.
Okay, so I'm guessing we haven't found any habitable planets quite yet.
That's a really good question. I don't think we've found any that we've sort of gone, yeah.
I think that would be headline news.
Yes, I think it would. They're all very far away, though. So when we think of habitable planets, it's not really for where we would live. It's just this idea of how many planets out there could have life, because then that gives us more of an idea of maybe where the aliens are. I don't want to mention the aliens, but maybe.
Well, that's actually where I want to go next. Yeah. So yes, maybe there are these habitable planets out there, but we might not be able to get to them because they're super far away.
They're really far away.
What are the chances that there are life out there somewhere in the universe?
So most astronomers would agree that there is life out there somewhere.
There is?
Yes, because the universe is really big. It's it is infinite. So the numbers of stars, and if all of those stars have maybe one or two planets, that's just ridiculous numbers. Even in what we call the local universe, the universe that we can see, it's millions, millions
and
millions.
It's so hard to grasp the concept of infinite space.
Yes.
Like it blows the mind.
I think the way that I think about it is just more than you could ever imagine.
Yeah.
There's more planets, more stars than you could ever imagine. But it's a double-edged sword. So the universe is big, so there's probably life. But the universe is big, so we probably will never meet it or talk to it.
Right, so we'll never meet aliens.
I don't think so. Interestingly, radio is probably the best chance we've got to talk to aliens.
Why?
Because we use radio light for communications. It's pretty likely, we don't really know the answer to this, but from what we know, that aliens probably do too. Radio light also travels great distances. So if an alien civilization is sending out a signal, they're probably using radio. And we can see radio at big distances, and we have nice big telescopes to detect it. So Breakthrough Listen and the Search for Extraterrestrial Intelligence, or SETI, do use radio telescopes, even here in Australia, to do these searches for what we call techno-signatures.
Okay, this is fascinating. Do you feel like we will make contact with an alien species in your lifetime?
No, definitely not in my lifetime. Astronomers don't like to talk indefinites, but that's it's just so unlikely. But it's still a really worthwhile endeavor because they're doing it in a very specific scientific way. And I think we should still look, because what if we did? Like, the chances are so tiny. But what if we did? And the other part of it is they help us a lot because as they're looking for these things, they're looking for signals that we don't really know what they're going to look like. So what they're actually really good at is getting rid of bad signals. So radio is affected by every phone, every TV, every aeroplane, every satellite. That creates kind of what we call radio frequency interference, but it's signals that mess up everything.
Right.
So they're really good at spotting those signals and removing them because they're trying to get something that's going to be so elusive that you need to have a really nice clean signal. So even though I don't think they'll find aliens, it's still a really useful, worthwhile endeavor.
How does this make you reflect on us as humans, the human race and our place among the stars?
I don't think about it too much, I have to say, because I think that would probably, wouldn't be a very productive work day. But I do think about it probably more than the average person, because when you're looking at space and you're looking at things that are thousands of light years away every day, you can't help but kind of think about how that impacts humans, or just impacts how you think about humans. And it's going to start off a bit depressing, but then it gets better.
Okay.
So it makes you think and sort of realize that if all life on Earth was wiped out right this second, there's nothing that would care or even notice because there's nobody watching us. There's no other life out there. There would be nothing left to think about it. So that's a bit depressing. But the flip side of that is that means that everything that has meaning in your life has meaning because it's important to you. And I think that's actually really powerful. Everything that matters to humans, it matters because we care about it. And I think that puts things into perspective, and even things like global warming challenges or keeping species alive, that's important because we care. And I think that's actually kind of brings us back to being really powerful and having a lot of agency in our lives. So even though it's a little bit depressing to think that if we disappeared, there's nothing that would actually care about us.
Unless you are inclined to believe in God, but yeah.
Yes, exactly. But it just means that we are kind of in charge of what goes on here. And I think that's really important. So we do make a big difference. We make, in fact, the only difference, really.
So if we are the only ones in the universe who care about us and what we do, and that gives us agency, should we bother wishing upon a star?
So this was actually something I recently came across because I now work on stars. And I think you think astronomer, you think star, right? Whereas actually a lot of astronomers don't work on stars.
They work on planets?
They work on planets or black holes or galaxies. So there's a lot of things that astronomers work on, but I work on stars. So there's the idea when you wish upon a star, right? It's a really nice thought. But I saw an Instagram the other day that said, when you wish upon a star, it's millions of light years away. So it's already dead, like your dreams.
God,
I know.
Brutal.
It's so rough. And I just thought, that doesn't sound right. But also it sounds really mean.
Yeah.
It just feels like, give us at least our dreams. Come on.
Wait, so why is that a misconception then?
So the stars that we see with our eyes are all inside our Milky Way for sure. And the Milky Way is only 100,000 light years across. So millions of light years is already wrong. But the stars we see with our eyes have to be pretty close because human eyes aren't that good. Mine especially, I wear glasses. So we can only see stars out to sort of maximum 10,000 light years. So if you think about it, the light has traveled 10,000 years to get to us. And if your wish travels at the speed of light, I'm not a wish expert, it takes another 10,000 years to get there. So in 20,000 years, is that star still alive? And you probably wished on one that's closer, right? Because that's the maximum distance. So your star that you wished on is probably closer.
Okay.
But stars live for the stars that we have nearby. I actually checked. I checked a catalogue. They all live at least a few 100,000 years.
Ah.
So if you make a wish today and it's 20,000 years until it gets to the star, you're still good. The star is still alive. You'd have to be pretty unlucky to choose like the one or two stars in the whole sky, which is 4,000 stars that you can see with your eyes.
Oh, wow.
That you'd have to be pretty unlucky.
Okay, so if you wish upon a star, you can actually see with your eyes.
Yes.
It's not dead,
It's not
which means
dead.
your dreams are not dead.
Exactly. And there are a couple of safe bets. So I looked this up too. Alpha Centauri is only about 4 and a bit light years away. And it's
Okay.
actually 3 stars, definitely still alive. Sirius is nearly 9 light years away, which is the brightest star in the night sky, definitely still alive. And Epsilon Eridani, I think, is the 3rd brightest star. And that's a young star, so definitely still alive. And the sun, of course, is a star, and it's only 8 minutes away. So if you really want to send your wishes to somewhere safe, it's going to last another 5 billion years or something like that. So definitely a few safe places you can send your wishes.
So does that mean if you wish upon, let's say, the sun, your wish will be granted in 8 minutes' time? Or if you...
Well, 16 minutes, I suppose, because by the time it's traveled. Well, we'd have to consult a wish expert on that one. It depends how fast you are at, really grinding for your dreams.
Choose the sun over a star 10,000 years away because you'll be waiting 20,000 years for the wish to be
exactly.
Have you ever wanted to go to space? You spend all your time looking up at space. Do you want to go there?
So I have mixed feelings about this because none of the things that I study are anywhere near us. So even if I did go to space, I wouldn't actually be much closer. But on the other hand, it is such a unique, there's so few people who have got to have that perspective. And I do think that would be amazing. So I think if NASA said, hey, would you like to go to space? I probably would say yes. Don't listen to this mum. I'm sure she doesn't want me to go because it is still really dangerous to go to space. But that would be I think there's nothing that humans have that compare to something like that. And it does make me think a little bit, damn, I wish I was alive when we did things like the moon landing because there hasn't been much, I'm a millennial, there hasn't been much in our lives that's quite that world changing. To know that humans stepped on the moon for the first time and to actually watch that, I think that would have been so mind blowing. And I wish we could go and have that experience again.
Laura, your work is mind blowing. It's been so fascinating chatting to you. Thank you.
Thanks for having me.
This is Conversations with Sana Kadar.
My guest on Conversations today was Dr. Laura Driessen, a radio astronomer who is cataloguing radio stars at the Sydney Institute for Astronomy at the University of Sydney. This conversation was recorded on the lands of the Gadigal people, and it was produced by Maggie Morris. Our executive producer is Carmel Rooney. I'm Sana Kadar. Thanks for listening.
You've been listening to a podcast of Conversations. For more Conversations interviews, please go to the website abc.net.au/conversations.
When a banana farmer in far north Queensland claimed to have seen a flying saucer and said it had left behind a mysterious mark, it unleashed a firestorm of hysteria.
Did you see it? What do they look like? Are they aliens?
That moment would haunt him for decades, not to mention inspire an international hoax. I'm Danielle O'Neill, and this story from Australia was where the modern crop circle phenomena all started. Search for Expanse on the ABC Listen app.